let's go ahead and take a look. So these are things to know, trig and triangles. This is your standard 90-degree or right triangle. So this one always has an angle right here, which is 90 degrees. Then we've got an angle theta. This is usually where we have them on projectiles. And the projectile is launched at this angle theta in the direction along the hypotenuse. So we might say that that projectile has an initial velocity that starts right here, and it's shot up, and then it kind of goes through its paces into on the other side and lands on the target. The opposite side of the triangle, I always tell my kids, the opposite side is the one that you always would use a bow and arrow to shoot at. So for example, if this is my bow and I've pulled this back, the arrow will always be shot towards the opposite side. I don't want to shoot it towards the adjacent side. I might hurt myself or somebody else. And so that's kind of what you'll see in terms of the opposite side, the adjacent side, and the hypotenuse. If you ever stub your toe and you go see the trainer at school, one of the things that the trainer might tell you is to go so, ka, toa. So you want to go soak your toe. And if you go soak your toe, then that's the same thing as sine is the opposite over the hypotenuse. Cosine is the adjacent. So this is the adjacent over the hypotenuse. And then tangent is the opposite over the adjacent side. So just a little pretty quick trick for you to go through and remember which side of the triangle is which. Remember, every triangle should add up to be 180 degrees. You already have 90 of it, so we can go ahead and just subtract 90. That leaves 90 degrees for our two sides here. If this angle theta, and then I've got another angle for this one, if this one is phi, if this one is 20 degrees, we know that this one's got to be 70 degrees. So just some triangle things that you really need to go through and make sure that you understand. All righty, here we go. Next thing, horizontal motion of a projectile. So let's say that I've launched a projectile, and this projectile is going along this side. And let's say that our velocity of the projectile along the hypotenuse is 10 meters per second. All right, cool. So let's go ahead and put in an angle. Let's say that this is 37 degrees. And they want us to figure out what is the initial speed of this projectile at an angle, at this angle of 37 degrees. So if I want the initial velocity in the x direction, so this is the initial velocity in the x direction, it's going to be equal to our original velocity. So that is this, and that's at the 37 degrees. And then if you notice this little angle kind of thing that you see here, we'll just say it's just that symbol. That means that we're looking at this angle. If you notice, it looks like a backwards C. And if it looks like a backward C, and we are on the side that it's touching that backward C, not on the longest side, but on the side that's the adjacent side to the angle, we're going to take our original velocity, we're going to take it times the cosine of the angle, which is 37 degrees. And here's the cool part. As that projectile moves through the vacuum of the Earth, and because remember, we're on the physics world, and on the physics world, unless they tell you that there is air resistance, you don't have to worry about it in AP Physics 1. So because there's no air resistance and it's moving through a vacuum, the velocity at any point, so the velocity here, so this would be Vx, the velocity here is Vx, and then even the final velocity in the x direction, these will always be the same. So they will not change. So they're always going to be the original velocity times the cosine of the angle. So that's the really nice thing about the horizontal motion of projectile, is it is constant. And remember, it is only constant if there is no air resistance. So if you want some problem that involve air resistance, probably the best thing to do is take AP Physics C. That's the calculus-based, and the calculus-based allows you to get in and really be able to take a look at how air resistance would affect the projectile. So if you're looking for that, that's the course that you want, is AP Physics C. Alrighty, so let's take a look at the vertical motion of a projectile. So we're only going to look at the up and down. So we know that this projectile is going to go up and it's going to come back down. But when it does that, we know that the velocity in the x direction we said is equal to v original times the cosine of the angle. We also said that on the other side is the opposite side, and this would be the velocity in the y direction. So that's the original velocity times the sine of the angle. So once you know which one's cosine, the other one is going to be sine. Just make sure it is the opposite side and not the adjacent. So here's our angle theta again. We could say that that's 37 degrees. And then in the y direction, we're going to take VO times the sine of the angle for our velocity in the y when we start right here. The problem with the velocity in the y is if we plot that velocity, so let's use a motion map. We're going to say that we are launching this and we start with a velocity in the y, and this is the original velocity, and it's represented by the length of this arrow. But as this projectile makes its way higher and higher, so here we are at 0 seconds, now the velocity in the y is right there, and we'll say that that's at 1 second. So this is at 1 second, this is at 0 seconds. And then let's say we get to 2 seconds and it's just got a little bit of speed left, so maybe it's right here. And so this is at 2 seconds, 1 second, and 0 seconds. And then finally at 3 seconds, we don't have any velocity at all in the y direction. Remember, our velocity in the x is always going to be the same. So it is always VO cosine the angle. Once we find this one at 0 seconds, I need to find out what is the speed at 1 second, 2 second, and then you'll notice at 3 seconds, there isn't any speed in the y direction. So Vy here is equal to 0 meters per second. So if we start with a projectile, and let's say that this is 30 meters per second in the upwards direction, if we move up at 1 second, we're going to notice that it's 20 meters per second. And then at 2 seconds, it would have a speed of 10 meters per second. And then at the very top, it's 0. And then on the way back down, it will have the same type of speed. So it's going to be 10 meters per second, but in the down. Here it's going to be 20 meters per second in the down. And then when it gets to the very bottom, it's going to have a 30 meter per second in the downward direction velocity in the y direction. So obviously the vertical motion of a projectile, it will decrease on the way up. So decrease up, and then it will increase on the way back down. And whatever velocity it had when it was launched, so remember we said it was about 30 meters per second, that's the same velocity it will have on the way down, but it will be the opposite sign. So our velocity here is negative 30 meters per second. So that's kind of the thing that you're going to see. All right, let's go ahead and take a look at some problems. So this is the very first problem that we're going to do. We have Ferdinand the frog is hopping from lily pad to lily pad in search of a good fly for lunch. If the lily pads are spaced 2.4 meters apart and Ferdinand jumps with a speed of 5 meters per second, taking 0.6 seconds to go from lily pad to lily pad at one angle, must Ferdinand make of his jumps. So let's always, whenever you start one of these problems, probably the best thing to do, go through and circle things that are important. So the very first thing that's important here is that 2.4 meters. That represents, and it says they are spaced 2.4 meters apart. So that is our change in position. Ferdinand jumps with a speed of 5 meters per second. So we know that our original speed or velocity is 5 meters per second. And it takes 0.6 seconds for the frog to go from lily pad to lily pad. So that would be our time or our change in time. So that is equal to 0.6 seconds. Now, we know that in order for the frog to jump, the frog's got to jump at an angle. So we're going to give that frog this angle, and we know that the original speed here is 5 meters per second. Jumps with this speed takes 0.6 seconds to go from lily pad to lily pad. They want to know at what angle must Ferdinand make for each of his jumps. So let's go ahead and draw kind of a diagram that's showing what's happening here. We know that the frog goes up and gets to this point, and then the frog goes back down. And these are the 2 lily pads that the frog is at. So the total distance between the two is 2.4 meters. So this is 2.4 meters from one side to the other. But we want to look at, let's go ahead and break this down. So we're going to look at this side, and this is 1.2 meters. We know that it takes a total of 0.6 seconds for the frog to go all the way across. So to go just this distance, it's going to take 0.3 seconds. And from the 2.4 meters and the 0.6 seconds, or from the 1.2 meters and the 0.3 seconds, we can find out what is the velocity of the frog. So we're going to find the velocity of the frog in the x direction. Why is that important? Well, remember, the velocity in the x direction for any of these problems is always going to be constant. So let's go ahead and we're going to say this is equal to, and we know that it would be the change in position divided by the change in time. So let's use the entire 2.4 meters, and let's use this change in time, 0.6 seconds, and see what we get. So we've got 2.4, and we're going to divide that by 0.6. All right, so if you are out there and you have a calculator, I want you to calculate that. And then down at the bottom, it says say something nice. If you can go ahead and do that and see what you get, and then let me know what your answer is, both in numbers and in units. That would be awesome. So we're looking for the velocity in the x direction. And we've taken the total distance, and we have divided that by the total time for the jump. And I ended up with 4 meters per second. So we know that for this triangle, we've got 5 meters per second in this angle. We have along the bottom, we do know what the velocity is in the x direction. So the velocity in the x direction is equal to 4 meters per second. So one of the questions that we could answer is, what is the velocity over on this side? So this would be the velocity, the original velocity in the y direction. But that's not what they wanted. They wanted to know at what angle must Ferdinand make each of his jumps in order to travel this distance. So because we already have 2 sides of the triangle, we should be able to find this angle. So we have to remember this would be the adjacent side. This is a hypotenuse, and because I have the adjacent and the hypotenuse, remember TOA. And we can find out using cosine what that angle is. So let's go ahead and do that. We know that the cosine of the angle is equal to the adjacent side, which is our velocity in the x, divided by the hypotenuse, which is our velocity, that's the original velocity. So here we go. We're going to take 4, and we're going to divide that by 5. And when we take 4 divided by 5, we end up with 0.8. So now we know that cosine of the angle is equal to 0.8. But in order to get the angle, we have to divide both sides by cosine. So typically when we do that, we use our notation like this, cosine -1. So we call that the inverse cosine of 0.8. So let's go ahead and put that into the calculator. If you have a calculator like this, the easiest way to do it is to hit second and then the cosine button, or you hit inverse and the cosine button. And then we're going to multiply that, or we're going to do the inverse cosine of 0.8. And when I do the inverse cosine of 0.8, I get 36.869 And probably the best thing to do is round these angles to 1 decimal spot. So this would be 36.9 degrees. So that's got to be the angle that he makes in order to jump from one side to the other. If that angle is steeper, okay, or if it's less steep, then the frog's going to miss. And so we want to make sure that we hit the right one. That's problem 1. Let's go ahead and take a look at problem number 2. Jack be nimble, Jack be quick. Jack jumped over a candlestick and did that with a velocity of 5 meters per second. The angle that we have here is 30 degrees. And they want to know, does Jack burn his feet on the 0.25 meter high candle? So Jack's going to go across, and then at the top here, we want to make sure that Jack has gone high enough that if there is a candle with a flame, this is 2.25 meters, that Jack is not burnt. So we've got to find out what is the maximum distance that Jack is going to go, or what is the change in the y position. So that's really what we're looking for. We do know the original velocity, and that is equal to 5 meters per second. We know our angle theta is 30 degrees, and we know that our delta y, or how high we need to go, is 0.25 meters. So we're going to solve for delta y. We're going to find out that if we are bigger or smaller than that. Notice I didn't circle this. This is just something that we need to know after we're done. So those, I typically have my students not underline or circle, either one. Alrighty, so the first thing we need to do is let's go ahead and find out, using our triangle, what the velocity is in the y direction. So we want the original velocity in the y direction. If we want the original velocity in the y direction, remember we said this is the cosine side. So we want the original speed times the cosine, I'm sorry, not the cosine, but the sine of 30 degrees. So our original velocity here is 5 meters per second. We're going to take that times the sine of 30. So in your calculator again, you can just take 5 times the sine of 30 degrees. Make sure you are in degrees and not in radians. And our original velocity in the y then is 2.5 meters per second. At this point, we know that we're going to go left to right at the same or the constant speed. We only want to know how high do we go when we're at the top. So at the top here, we know that our final velocity in the y direction at the top should be 0 meters per second. Because as you travel up, you decrease your speed until you hit 0, and then you'll fall down, where your velocity then, or your speed, will be in the down direction. And so it would be negative with our velocity in that direction. So this is our original velocity in the y direction. It is 2.5 meters per second. We know that the final velocity in the y direction is equal to 0 meters per second. So this is where we're going to go back to kinematics, and we have to use our kinematics to figure out what that distance is. So there's several equations that you can use. We know that if we have time in the equation, we can't use it because we're not given time. So, and we don't need to find time. We're going to use the equation, the kinematics equation, that does not have time in it, and that is Vf squared is equal to Vo squared plus 2 times the acceleration times that change in position. So because we're traveling in the y direction, one of the things I like to do is say this is the final velocity in the y squared. That's equal to the original velocity in the y squared. And then we're going to take this and we're going to say this is plus 2 times g, which is gravity, times the change in the y position. So if Jack is moving upwards, we're going to make upwards the positive direction, which means that gravity here will be in the negative direction. So this is going to be negative 10 meters per second squared. And yes, you should always use negative 10. It is allowed on the AP Physics 1 test, and it will make everything a lot easier as you go through. Okay, so our final velocity in the y direction we know is 0. the original velocity in the y direction we said was 2.5, and we're going to square that, plus, and then we've got 2 times negative 10 times that change in our position, which is delta y. Back to the calculator again, we're going to take 2.5 and square it. And once we square that, we get 6.25. We'll move that to the other side. We get negative 6.25, and that's equal to negative 10 times 2, which is negative 20, times delta y. So notice that we're doing everything in meters here. We're going to now try to find out what is that delta y. Okay, so we're going to find out what is delta y. So we're going to take 6.25 and divide that by 20. When we divide it by 20, we get a delta y that's positive, which is good because we're measuring from round up. And that value is 0.31 meters. So if that's true, Jack did not burn his feet on the 0.25 meter high candle. At this point, I'm going to stop to see if you have any questions or not. So I'll give you a second to kind of take a look at what you've been writing down and see if you have any questions. Okay, I don't see anybody has any questions. I think what we're going to do is go ahead and we're going to skip problem number 3 and actually go to an AP problem. So this is an actual AP problem that was given. And this is a drinking fountain, and you'll notice that the drinking fountain projects water at an initial angle of 50 degrees. So this is equal to the angle that we usually use, and we typically use the angle theta or the Greek letter theta in order to signify that. The water reaches a maximum height, so this would be our delta y, and that's equal to 0.150 meters at the point of above the point of exit. So from here up, they've showed you that this is 0.15 meters. Now, on the AP test, they have you do a lot of deriving. So they want to make sure that you understand the physics. And they want to make sure that you don't have a number necessarily that you're solving for. So they will ask you to derive some things. So they want us to express our answer in terms of VF, VO, H, and any fundamental constant. So probably the constant that you typically will use in a lot of these is going to be gravity. So if it's a projectile motion problem, we know it's on the Earth, there's probably no air resistance, and they said that right here. Air resistance is negligible, so the word negligible, if I could say it, means that you can ignore it, so you don't need it at all. Let's go through and figure out the equation for the speed at which the water leaves the fountain. So we want an equation for the speed that the water leaves the fountain. We know that the water is leaving the fountain in this direction. And so we're going to go ahead and make our angle here. And we're going to make our triangle. We know that the angle here is 50 degrees. And we know in the y direction, the height that it attains, our delta y, is equal to 0.150 meters. We don't know what this velocity is, so we have no clue what this original velocity is, but we do know that the original velocity times the sine of our angle, which is 50 degrees, is the original velocity in the y direction. So how did we know it was sine? Remember, it is the opposite side of the triangle. Okay. From that last problem, we also said that the velocity final in the y direction is equal to 0 meters per second. So let's go ahead and try to find out if we can get an equation for VO. Okay, so we want just the equation for VO. And so we're looking to see if we can just solve something for this. And remember, this whole thing here is equal to the original velocity in the y direction. All right, so let's go ahead and use remember the equation that we just used, which was the final velocity in the y direction squared is equal to the original velocity in the y direction squared plus, and then here we're going to do 2 times gravity times the change in our position. If we say that up is positive, we know that we're going to have to make this negative at some point. So we're going to go ahead and rearrange our equation. So VFY squared is equal to VOY squared plus 2 times negative G times delta Y. Now at this point, because we know we've got to solve for VO, we want to substitute in what we have here for VOY. So here's our VOY. We need to put this in for that. So let's go ahead and go over here. So this is the final velocity in the y direction squared is equal to, and we're going to do the original velocity times the sine of 50 degrees. And then we're going to subtract from that 2 times gravity times, and now instead of delta y, remember they said that they wanted us to use h. So we're going to subtract 2 times g times h. We also said, oh, we've got to square this. So this whole thing we need to square. So at this point, we also need to go back and realize that this is 0. And so 0 is equal to VO sine of 50. And we want to square this, minus 2GH. Let's move the 2GH to the other side. So now we have 2GH is equal to VO squared times the sine of 50. And we're going to square it. We need to go ahead and let's take the square root of both sides. So this would be the square root of 2GH, and that would be equal to VO sine of 50. And the last thing we need to do is we want to find the speed at which the water leaves the fountain, so we just want VO all by itself. So VO is equal to the square root of 2GH all over the sine of 50. So that's a lot of work, and that'll probably get you a couple of points. So typically what they'll do is they will look for some sort of understanding that you need to make VOY into VO sine of 50. So that's probably 1 point. So let's go through and we'll do points in a different color here. Let's change the pen color to blue. All right, so we probably would end up with a point for just substituting this in. So we're going to put +1 right here. Okay, so it's not really the actual rubric. Instead, I'm just kind of helping you kind of see where you can think about where points might be. At that point, they would also say you need to use this equation and plug in your variables that you can use to solve for VO. And so probably this equation right here is what they would be looking for, or something that would lead to that equation. And so that would be a point. And then down here, they would say, okay, we need the final equation. So this would be the point. So somewhere around 3 points, 2 to 3 points typically for a derivation that you've done. Does anybody have any questions on this derivation and what we did? So I'm going to just take a look over here on my other screen and see if anybody has anything they have. Okay, we going too fast, too slow? Everybody good? All right, cool. So this is our equation. VO is equal to the square root of 2GH over the sine of 50. Let's go ahead and move on. And from this, we want to calculate the speed. So remember our equation was square root of 2GH over the sine of 50. So our original velocity is equal to the square root of 2GH all over the sine of 50. And we do have a question. So, hey, hi, Taylor. This one is not part of Newton's laws. This one is actually on projectile motion. So we're looking at how things are launched and then using kinematics to figure out where they go. We're actually doing Newton's laws next week, and we'll start going through all of those. You're welcome. All right, here we go. So let's go ahead and plug everything in. So this is equal to, so remember, they want us to use our equation and find out the speed at which the water leaves the fountain. So this is 2 times 10 times our height, which was 0.15. and we're going to divide that all by the sine of 50. So we need the square root, so let's go ahead and hop on the calculator here. We're going to do the square root of 2 times 10 times 0.15. And if you do that, you get 1.732. So 1.732. And we're going to divide that by the sine of 50, which is 0.77. So this is 0.77. So 1.732 divided by 0.77 gives us an original speed of 2.25, and then that would be meters per second. So far, we're on our way. When it says calculate, they do want to make sure that you have plugged your variables in. So let's switch back over to red. We'll put red in on this one for where your points come from. And so we're looking for, did you use the equation properly? So did you plug everything in? And if we did, you get a point. From there, it's really just, did you get the right answer with the correct units? So sometimes they will give you a point for the unit and the answer. Sometimes they just give it for the number or the magnitude. This meters per second, if they run out of points, they need more points. In the end, they might go back and say all of your units are correct for all of your answers in this this part of this one problem. So that's what they'll typically do. So usually you'll see about 2 points for these. All right, cool. This one is a really great problem. So this is one that used to be on the AP Physics B test, which I've seen them kind of modify a little bit to put it on the AP Physics 1 test. So I'm going to switch back over to blue again, just because it's a little bit easier to see, I think. And the very first thing that they want us to do here is we've got to go through and read a little bit about what's going on. So we had somebody that just came in and asked about Newton's laws. So we are actually going to have to use something from Newton's laws in order to figure out this very first part. So it says a ball of mass, and so we know that the mass here is 0.5 kilograms initially at rest. So we know that the ball is initially at 0 meters per second, is kicked directly to a fence at a point 32 meters away. So we know that there is some sort of change in position equal to 32 meters. We're not sure if we need that or not yet, so shown above. So on the actual problem, this picture was above everything else. The velocity as it leaves the kicker's foot is 20 meters per second. So it was initially at rest, but then the person kicked it. Okay, so what we've got to do is we need to now change and say that this is the original velocity of the projectile, okay? And that is after it makes contact, or just at the same instant that it makes contact with the foot. 37 degrees, that is our angle theta. And it's above the horizontal. The top of the fence is 2.5 meters high. So we know that that is a change in vertical position. The kicker's foot is in contact with the ball for, so this is a time, 0.05 seconds. And it says the ball hits nothing while in flight and air resistance is negligible. Okay, so obviously this person's maybe on the moon kicking the ball over the fence. I don't know. Probably on the earth because we're going to need to use gravity. So it's just a really great ball. It doesn't have any air resistance at all. Okay, so its coefficient of drag would be very small. Okay, here we go. It says derive the magnitude of the average net force exerted on the ball during the kick. Express your final answer in terms of m, v, t, and n fundamental constants. Okay, so we want the average net force. So average net force would be F, average. And we know that force is equal to mass times the average acceleration, which is AVG. So even if you haven't been in dynamics yet or in forces, you know that equation. So F equals ma, it's that classic equation. One thing that you do know is acceleration is equal to the change in velocity over the change in time. And remember, that is the average, not the instantaneous acceleration. So that's the average acceleration. We can now plug this in for what we have here. So we can say the average force is equal to mass times the change in velocity, all divided by the change in time. And so at this point, we can find out if we've answered everything in the right way. They wanted us to do this in terms of m, we did that, v, we did that, and t, and we did that, and any fundamental constants. So there's no fundamental constant here. We just have our equation. If you actually go through and solve this, you would find out that this is 0.5 kilograms. We know that the change in velocity from the very point where we just about had our foot on it to where it is now traveling at 20 meters per second would be a change in velocity of 20. We're going to divide that by the time, and we said it was 0.05. And if you do all that math, you should end up with 200 kilograms times a meter per second, which would be a Newton. And so now we know the force we've kicked that ball with. Let's go ahead and go to the next part. In the next part, it says calculate the magnitude of the average net force. So we just did that. So we went ahead and we plugged everything in for it. So we're set there. Next part of the problem, it says determine the time it takes for the ball to reach the plane of the fence. So we want to know if it travels 32 meters and it's launched at 20 meters per second, how long does it take to actually get to the fence? The best thing about this problem is we just talked about the velocity in the x direction. So that would be the velocity along this bottom line here. Remember, here's our angle, and this is 37 degrees. This would be our original velocity, and our original velocity is 20 meters per second. It was the final velocity for the force calculation, but now that same speed becomes the original velocity for the projectile or for the ball trying to go over the fence. This side would be the velocity in the x direction, and we really need that because we already know what the distance is. So we know the delta x, and so the displacement is 32 meters to the fence. We want to know how long does it take for it to get there. So that's what they're looking for, the time. And it's super easy to do. So Vx, remember, is equal to the original velocity. And there's that c again. So this must be the cosine side, the cosine of the angle. If you want to just stay mathematical, you'd say, well, this is the adjacent side, this is the hypotenuse. And so we've got VO cosine of the angle. 20 meters per second times the cosine, and then they give you 37. So they always tell you what these angles are. So if you do have a calculator that doesn't work, you could look on the AP Physics equation sheet. But most of the time, you're good enough that you'll remember to bring a backup calculator. But if not, just know that it's there. So this one is actually 15.97. And so we're going to call it 16. We're going to go ahead and put 16.0 meters per second. And that's the velocity in the x direction. Remember, the velocity in the x direction is constant. Okay, so that's just delta x over delta t. They want to know what is the total time to get from here over to here. That doesn't mean that the ball's doing this. Okay, so that doesn't mean that. It just means that the ball is traveling. It might go over the fence. It might run into the fence. It might land short. We just don't know yet. That's one of the things that we're going to have to figure out. But we do need the total time to get to the fence. So let's go ahead and rearrange our equation for time. So delta t here is equal to delta x over our original velocity in the x direction. So that's Vx, and it's the same velocity all the way across. So we're just going to leave it Vx. This is 32 meters, and we're going to divide it by our speed, which was 16 meters per second in the positive direction, which makes it our velocity. And 32 divided by 16, hopefully you don't need a calculator for that, that is 2 seconds. So we know to go from this point right here all the way over to the fence, that will take 2 seconds. The next question that they're going to ask is, derive an equation that may be used to determine if the ball will hit the fence. So we want to know, what is the height when we are at 2 seconds? So when we have a travel time of 2 seconds, so travel time, we know that, and that's equal to 2 seconds. They want us to find out what is the equation that we can use to find out if the ball actually hits the fence there. So we have a couple equations that we can use. We can think about VF is equal to VO plus acceleration times time. The problem with this time equation is it doesn't have any distance in it or not, okay? So ideally what we need here is we can't use this one. We can't use the one that's VF squared is equal to VO squared plus 2AD because that one doesn't have time in it. So the only other one with time is the change in the y position is equal to the original velocity in the y direction times time plus 0.5, or well, let's just do this, 1/2 of the value for gravity times time squared. Okay, so we do know the time, we do know the value for gravity, and we can probably pretty easily find out what the VOY is. Okay, so we want to know if the ball will hit the fence. So we want to know what is delta y. Well, guess what? We've really just gone ahead and we've solved that equation. So delta y is equal to VOY t plus 1/2 gt squared. The only thing that we need to do, though, is they wouldn't give you full credit because we have not used the actual angle here. So we need to tell what is this. So VOY should be equal to, so let's make our triangle again. This is 20 meters per second, so that's equal to VO. And then we have our triangle here. And we know at this point, this is 37 degrees. So VOY, so the original velocity in the y direction, is going to be equal to the original velocity times the sine. Remember, this is that opposite side of 37 degrees. So now we can put in delta y is equal to, and then we're going to do VO sine of 37 times the time plus 1/2 of gravity times time squared. The big deal here, though, is if we make this velocity positive, we're going to need to make gravity negative. So if you're going to do plus 1/2 of g, you're going to want to put that negative in at that point. All right, so now we have our final equation, and I bet the next thing they're going to do is ask us to figure out, does the ball hit the fence? And if not, how far above the fence does it pass? So let's go back and take a look at our equation here. It is VO sine of 37 times t. So we know delta y, so the change in position, is equal to VO sine of 37 times the time minus, and then we're going to do 1/2 of gravity times time squared. So notice I went ahead and moved that negative in front. If you don't do that, you're really going to get the wrong answer. So our original velocity we said was 20. We're going to take that times the sine of 37, and we'll have to multiply that times the time. Remember we said that it would take 2 seconds to get to the fence, so we're going to put in that 2 seconds. Then we're going to subtract from that 1/2 of gravity, which is 10 meters per second squared, times our time again, which is 2 squared. So let's figure out at what position is it going to be. So that's going to be our delta y. The other thing you could have done with this is you could have said my y final is equal to my y original plus, and then did the VO sine of 37 times time minus 1/2 of gravity times time squared. Your original y is 0, so that's your YF. We just moved it to say delta y. It just makes it easier. So let's take 20 times the sine of 37, and then we're going to multiply that times 2, and we get 24.07. So this is 24.07. I know that's a big number, but remember we're going to subtract something from it. So that's 1/2 of 10 times 4, and that gives me 20. So this is 20 meters. And so now when we do our math, we'll notice that we're going to have 4.07 is our change in position. So we know that when the ball is traveling, when it gets to the fence, it is at a total height from here all the way down to the ground of 4.07 meters. And because it's at 4.07 meters, we can say it is above the fence. So we can write the word above. And we want to know how far above is it. So we're going to take 4.07 minus 2.5. And so 4.07 minus 2.5 is going to give us 1.57 meters above the fence. So now we know exactly how far above it is over the fence. The very last thing that they want us to do here is it says on the axes below, which are here, they want us to sketch the horizontal and vertical components of the velocity of the ball as functions of time until the ball reaches the plane of the fence. So we said that time for it to get to the fence was 2 seconds. Notice that they give you all the way out to 4 seconds. So that's a hint that you have to be really careful. We know we went that 32 meters. We knew that it took a time equal to 2 seconds. So here's what we're going to do. Let's go back and see what that velocity was in the x direction. So we're going to move our way back, and we see that the original velocity in the x direction was 16 meters per second, and we know it doesn't change at all. And because it doesn't change, when we do this part of the problem, we're going to go up to 16. We're going to put a dot right at the 16, and then we're going to move over to 2 seconds, and we'll put another dot, and then we need to draw a straight line. So a ruler would be super important here so that you can draw that straight line. So that's our horizontal component of velocity. The weird thing is the vertical component of our velocity is not going to be a horizontal line. We know that it starts with a somewhat large velocity, and then that velocity decreases uniformly. So let's go back. We see that our original velocity in the y direction, okay, so our original velocity in the y direction, remember, was 20 times the sine of 37. But it's not times 2, so be careful. We don't want this. We want just 20 times the sine of 37. So let's go back here, and we want the original velocity in the y direction, which is the original velocity times the sine of 37 degrees. Whoa, that was wrong. 37 degrees. Our original velocity is 20 times the sine of 37 degrees will give us that velocity in the y direction. So I'm going to take 20 times the sine of 37, and I end up with 12. So I know that I start at 12 meters per second. So I'm going to put a dot. So this is 10, 11, 12. And as I'm climbing, remember that I lose 10 meters per second every second. So one of the things that you can do to do this is go over 1 second and then put a dot right where the 2 would be. Why did we do that? Because we know that the acceleration due to gravity is equal to negative 10 meters per second per second. And I started at 12 meters per second at 0 seconds. After 1 second, what would my speed be? Well, it would be a speed of 2 meters per second, and it's still in the positive direction. After that, I've got another second that goes by, and so I can go down another 10. If I go down 10 from positive 2, that's going to take me all the way down to negative 8. And so I'm going to come over here, and I'm going to put a dot at negative 8. Remember, we don't want anything past this. So even though they gave us all of this space, this is not one of the problems where you have to fill up half the graph. This is one where you're just plotting these points, and you're going to really just go through and connect the dots. Another straight line. Whoops. Oh, here we go. So we want to make the straightest line that we can. The slope of this line, coincidentally, is the acceleration due to gravity. You'll notice that it is a slope of negative 10 meters per second per second. So that is really the end of this problem. And that is the end of kind of what I've got for everybody. And so I think at this point, what I like to do is if you have any questions, about anything that we did. I'd be glad to go back and explain anything that that you saw here, and I'll quit doing that because that's really annoying. Does anybody have any questions? Any questions about angled projectiles? So I know there's usually an equation that a lot of people like to memorize, and it's called, oops, I'm going to back up one more time so that I can pick up the pen again here. And that is called the range equation. You do not need to memorize the range equation. So there is an equation, it's called the range equation, and it is something that you can memorize. It basically just says if you know the angle and the launch speed, you can determine very quickly how far it will go. They will never ask you to solve anything using the range equation. They're always going to have you do something very similar to what we did here. They might even have you explain using a paragraph format kind of what happens as you go through and take a look at, they might say describe in a paragraph length format using any diagrams or anything else that you want to, the difference between velocity in the horizontal direction and the velocity in the vertical direction. So you could go through and do that pretty easily to kind of describe the difference between the two. They could have asked you to explain why this does not hit the fence, and you'd have to go through and explain that, but those are typical things that they'll have you do. Okay, so I'll tell you one more thing that is kind of helpful. You probably will not see anything where they're going to launch something off of a cliff, because if you launch something off of a cliff, you actually have to treat it as a couple of different projectile problems. You have to treat it as a parabola and then add that to the fall. And so there's a little distance here that it travels. That tends to be a little bit more complicated and something that goes through.